Let's see if I can do this video with no or very little editing. I'll just talk about a few of the design considerations of a very simple 7 MHz CW QRP transceiver. You might know them quite familiarly as the Pixie. You often see them on eBay for just a few dollars. And as far as value for money goes, the kits are pretty good. You probably can't buy the components for less than what you can get the whole kit. The most valuable components there are the crystal for 7023 MHz in the 40 meter band and the LM386 audio amplifier chip. Also some RF chokes and capacitors are also useful. Anyway, the general principle of the Pixie is that you have one transistor as a crystal oscillator. There's also another transistor as the RF power amplifier. The circuit you see here is a bit different. It's just one transistor for the crystal oscillator, and that feeds straight to the antenna here. I've previously described it, a one transistor CW transmitter video, so look up that. Anyway, I'm also using that transistor as the diode detector, and it's non-linear. It works because the incoming signal comes through here through the pi section low pass filter. This part of the transistor operates as a diode. You also have it generating RF from this crystal oscillator, and when it's in receive, there's a resistor from the emitter to earth, and in receive there's some audio. It's very low level, but there is audio present at the emitter stage, and so that's where you feed that into the audio amplifier. The Pixie uses an LM386 audio amplifier. This particular design, which I won't go into too much detail, is just two transistors, and I can actually hear signals on it. It is very faint, but it does work. And that's even with low impedance headphones, which I'm using in the emitter circuit of the second audio transistor. If you've got a crystal earpiece, you can get away with not using the second transistor here in the audio and just having the crystal earpiece across here. It's high impedance, it's more sensitive, so you can get away with it. Another difference between this and the Pixie is that the Pixie does the diode rectification thing in the second transistor. That's the power amplifier transistor, whereas this does it all in the crystal oscillator transistor. Some other problem with the Pixie, particularly if you are near a strong AM broadcast station, is overload. And yes, there's a small amount of filtering provided by this filter, but it's a low pass filter. It's really designed to be knocking off the harmonics which are above your transmitting frequency. It really doesn't attenuate very much at lower frequencies like the AM broadcast band. So what you'd really need is some form of band pass filter here. Another thing you can do, if you've only got one strong station that's causing you problems, then you have, across this RF choke, you have a series tuned trap. You'll need to design that specifically for the frequency of the broadcast signal you want to eject. I haven't actually seen this in other Pixie type designs, so that if you have a Pixie, you should be able to apply this approach to that as well. Anyway, I'm using 10 microhenry in series with 1.3 nanofarads. And if you have a look at some online calculators for reactance, well, it's actually tuned circuit calculators, so you need to know frequency, inductance, and then it will tell you the resonant frequency, and you want it to resonate at the frequency of the offending station, which in this case is 1377 kilohertz. Anyway, I found that 10 microhenry in series with 1.3 nanofarads was fine. Of course, you can't buy 1.3 nanofarad capacitors, so what you do is you get, say, a 1.2 nanofarad, which is a preferred value, and you put 100 picofarad in parallel with that. Or if you still don't have that, then 1.2 or 1 nanofarad or 1000 picofarad as that is, and then you put, let's say, 270 picofarad or maybe 330 picofarad. Either of those should be near enough. Anyway, you have those, they work in parallel, and they give you 1.3 nanofarad. Or if you've got 2.7 nanofarad, then you just put them in series, and that halves the capacitance, and that will be near enough. So that is a series tuned trap. Really important if you have problems with AM breakthrough, but only works for one station. One possibility, if you had problems with a lot of AM broadcast stations, is instead of having a low pass filter here, make it a tuned circuit so it is super selective and only admits 7 megahertz signals and rejects all the rest. So there's some other ideas you could do here. So that's a very basic QRP CW transmitter. I've done previous videos on it. It's not the sort of thing that you'd be using for serious CW operating. It's more a novelty thing. If you know that there will be people listening out for you, like if you're doing a SOTA summit or national parks, then something like this would be okay, especially if the people at the other end are in quiet receiving locations. It's only about half a watt output, so if you've got people at home, especially if they're in a suburban noisy environment, that might not be so good because, you know, noise. If you can get 3, 4, 5 watts, then that can be a lot better. Now, of course, if you want something other than these two transistors, then you use something like an LM386 audio amplifier. I did a video years ago on taming the LM386 because you sometimes see circuits that are super simple, super simple. And yes, that might have worked for the builder, but with the LM386 there's a lot of extra components that my experience is you do need to add, otherwise the thing will just oscillate. Another problem with it is it can pick up AM broadcast stations. In fact, I think I've seen circuits of LM386s used as AM receivers. I could be wrong, but anyway, the transistors in them do respond to RF. So you really need capacitors across the input. And when I say across the input, not just across the input connections, but they've got to be right at the pins of the IC. And a suitable capacitor value would be 1 nanofarad. And that would go from pin 3 of the LM386, that's the input pin, to the earth, which is basically pins 2 and 4, which are earth. So you can have very short leads, and that will help stop RF getting into it. I might as well just draw a very quick diagram. I won't draw the whole LM386, but there's pin 3, that's your input lead, and it's 2 and 4 here. So you have your 1 nanofarad right here. Another thing I find is that LM386s are designed for use with some sort of volume control or potentiometer on pin 3. You probably don't need that for QRP rigs because the gain of the LM36 is just enough to hear signals. You're probably not going to need to turn the volume down, especially if you're not using any sort of audio preamp, so you don't need a variable capacitor. But I do still suggest having a resistor across the input, something like 10k, and that will help. Then there's your series capacitor, your coupling capacitor. That comes from, in this case, the emitter of your transmitter, which we're also using as a diode detector thing. Anyway, the capacitance value for a lot of audio type applications, you see it might be 1 microfarad or 4.7 microfarad, but for radio stuff, especially for CW, you want a low frequency roll-off, and you can have problems with AC hum if you have a too big a capacitor that lets a lot of low frequency stuff through. So you might only have it as 100 nanofarad because that will then cut off a lot of the low frequency signals. Now there is one little complicating factor. sometimes you do want to hear low frequency, low audio signals, especially if you've got a case here where you don't have much of a frequency offset. Your frequency offset here, without any special switching, might only be 300 Hertz or something like that, which is really, it should be higher. But without much of an offset, you're just relying on the pulling of the crystal when you go from transmit to receive. And if you don't have a proper offset built in, then you might still want to be hearing low audio frequencies like 100, 200 Hertz. So to get around that, you might instead decide to use a bigger capacitor here. But you're opening yourself up to hum problems, as I mentioned before. Or another alternative, and this is better, is to put a small variable capacitor in series here, or if you're too poor to have a variable capacitor, then just switch another capacitor in series. I'll just draw you a quick diagram. Here's the crystal. This might be one capacitor, 220 picofarad. You might not even need that at all. You might have a 33 picofarad here, and then you just have a switch across here. So if you have the switch open, then you've got the 33 picofarad in series with the crystal, etc., and that gives you a slightly higher frequency, maybe a kilohertz higher. And then you just short it, and then it shorts out the 33 picofarad, and that drops the frequency, slightly lower frequency. So you can get a bit of a frequency offset if you do that. Anyway, getting back to the LM386, another issue is pin 7 down to ground. Definitely need a capacitor here, maybe 10 microfarad. A lot of circuits I've seen don't have that. Don't build your circuit without it. They're just taking shortcuts. It's shoddy and it might not work. The LM386 is quite a temperamental beast. If you take shortcuts, sometimes it works, sometimes it doesn't. So just be aware of that. And of course, you've got the usual thing. Pin 5 is the audio output. You might have 100 microfarad here. Maybe if you're only interested in the higher frequencies, like around 1 kilohertz, maybe you can get away with 10 microfarad. Especially if your headphones are like 32 ohms, something like that, rather than an 8 ohm speaker. So something like 10 or 100 microfarad here, okay, but make sure that from pin 5 to earth, you have your series resistor and capacitor. That resistor is about 1 ohm. I think it's about 1 ohm. Maybe some circuits I've seen have been 10 ohm. Anyway, that's in series with, say, a 100 nanofarad capacitor. That just stabilizes things a bit. Now from pin 6, of course, is the supply rail. Now, of course, we didn't mention pin 1 and 8. Well, since gain is really at a premium, since all the gain in the receiver is coming from the LM386, a quick trick to increase the gain is to put a capacitor across 1 and 8. So I think it's about 10 microfarad. A small electrolytic or tantalum would be fine. Always have that. Pin number 6, that's your supply rail. You could try connecting it directly to your 9 to 12 volts, or you might want to put a resistor in here, maybe 10 ohms. Now, of course, there's a couple of things missing here. First of all, you need an electrolytic capacitor. Make it 100 microfarad, 220 microfarad, 470, something like that. And that goes from pin 6 to earth, and keep your leads short once again. And that just stabilizes things, and you probably want another capacitor here, similar value, 100 microfarad, something like that. Really not critical. Main thing is there's a good value capacitor here, as you can get all sorts of low frequency audio oscillations if you don't get your decoupling right. So yeah, a lot of things can derail an LM386. In fact, there's more problems than components in some of these circuits. You can get AM broadcast pickup reception that you don't want. You need to shunt all that to earth with a capacitor like this. You can get hum if your capacitor value here is too high. You can get motor boating and oscillation, and that's if your decoupling is bad. And yeah, so a circuit that looks simple can have a lot of problems if you don't pay attention to all this sort of stuff. Here's a example Pixie circuit board. I've taken all the bits off, and it really takes a long time to strip the parts off. These circuit boards are high quality, they are through hole, and that's a bad thing if you want to take bits off the circuit board. Removing the IC socket to salvage it is particularly hard, and you might melt it. So that makes it a problem if you want to do lots of modifications and upgrades to your Pixie. Another option, I still recommend buying the Pixie kit because it's such good value, but if you've got a other audio amplifier, like what you see on the left was got out of a pair of computer speakers, then you can also use that for a receiving part of a very simple QRP transceiver. Just connect the input via your 100 nanofarad capacitor to the emitter, just like the circuit that you saw before, and you should be able to get some audio out of it and be able to hear CW signals. Just bear in mind keeping leads short. The leads you see here are too long, but I attended to a lot of things like the decoupling on the amplifier circuit. There's a few parts on the underside of the board that you don't see here, especially the 1 nanofarad across the input of the audio amplifier. That was very important. Also providing a capacitor across the output, that was also important to steady it down. For more information on the transmitter side of this, have a look at my previous video that was all about building things on chopping boards. And I did actually have a contact with this rig, though it's a bit on the low power side at only a few hundred milliwatts. The signal comes in through the low pass filter. The transistor operates as the crystal oscillator. You can see the crystal in the top left. The audio is taken out from the emitter, and it follows this rather long wire into this IC audio amplifier. The chip looks like an LM386, but it isn't. It's actually a stereo IC amplifier. I think it's used in a pair of cheap computer speakers, something like that. Anyway, I'm only using one part of it, one channel, and then that feeds the headphones. It has slightly more gain than the two transistors that I mentioned before. If you look carefully, you can see there's two RF chokes in the picture. One is the normal type that goes from the collector up to the positive rail. That just provides DC RF isolation. And then there's another that's tack soldered, and that's in series with a capacitor. In fact, two parallel capacitors that shunts all the unwanted signals on 1377 kilohertz, which is a strong local AM station, to RF Earth. I needed to put that in, otherwise the broadcast station would just overpower the receiver. So, just thought I'd talk about a few of the things if you're building ultra simple QRP rigs. As I mentioned before, they're not serious transceivers for making contacts and getting contacts all the time, but they are a lot of fun to build, and in certain circumstances like prearranged contacts, especially if the people receiving you aren't quite receiving locations, you can still span hundreds if not thousands of kilometers. Now, if you want to learn more about QRP, then don't forget my book, Minimum QRP. You can get it as an ebook or in paperback, and just search the title on Amazon or visit my website vk3ye.com.